All right, so we're starting off with section 1.9, hybridized atomic orbitals. And we spoke about this last class, and I said, well, if you just look at the electron configuration of carbon, which is 1s2, 2s2, 2p2, these are the valence electrons, the ones with the highest principal quantum number. And if we look at those valence electrons, which are shown right here, you see that we only have 1, 2 unpaired electrons. And that, first of all, doesn't explain how carbon could make 4 bonds. And as I told you, carbon always makes 4 bonds when it is neutral. And so what needs to happen is one of the electrons from the 2s orbital gets excited into a 2p orbital. And you see the process of excitation occurring right here. And now look at what we have. We have a total of 4 unpaired electrons. And that's great. There's nothing wrong with that. That's a good thing. But it still, so it explains how the carbon can form 4 bonds because it needs to have 4 unpaired electrons to form 4 bonds. However, these 4 unpaired electrons are in different types of orbitals, aren't they? We have 1 electron in a 2s orbital, and then we have 3 electrons in 2p orbitals. We know that the shapes of these orbitals are different, aren't they? The 2s orbital is a sphere, and a p orbital looks like a dumbbell or a peanut or something like that. And so if we were to overlap 1 sphere and 3 dumbbells, that's not going to give us a tetrahedral arrangement. So it doesn't explain why the bonds would all be equivalent and spread out in this tetrahedral arrangement that we see here, where the bond angles are 109.5 degrees. And so the answer is that the orbitals must undergo what's called hybridization in order to form 4 equal atomic orbitals with a symmetrical geometry. And we call these orbitals hybrid orbitals. And the reason why is because we're mixing orbitals, aren't we? We're going to mix 1s orbital and we're going to mix the 3 2p orbitals to make 4 degenerate or equal energy sp3 orbitals. And you see the 4 sp3 orbitals here, and each one of them has an unpaired electron. And that, my friends, explains why a carbon atom has 4 unpaired electrons of equal energy in the same type of orbital. And that explains why the carbon can adopt a tetrahedral geometry. Now, what does the sp3 orbital look like, the hybrid sp3 orbital? And we went over this a little bit during the last class, but if you think about it, you're mixing 1 s orbital, so 1 sphere, with 3 dumbbells. And what you end up with is an orbital that looks like the one that's shown on the bottom of the page here, where I wrote sp3. Now, there's a much simpler way to represent the sp3 orbital, and that is to simply draw a lobe like this. So the way that I will always do it is I just draw a lobe like this and I write sp3, okay? And that way the reader knows that they're looking at an sp3 orbital. The whole idea of adding the second lobe here out of phase with the other one, we don't even include that when we're drawing, okay? Now in the book, they might include it from time to time, but when you're doing your own drawing at home, it's kind of hard to add the other side of the hybrid orbital. And if you have to draw an sp2 orbital, you'll do something similar. You'll draw something like this, and you'll write sp2. And the same thing applies for an sp3, or sorry, an sp. You would just write a lobe like that, and you would label it. And that way the reader knows what they're looking at. So let's move on from there and take a look at our methane molecule again. So this is that molecule that I held up before I started recording this morning. This is nothing more than a model of methane, right? We have a carbon with a hydrogen bound. We have another one here. We have one going back, and then we have one over here. And what they're showing is that each one of these hydrogens is a 1s1, right? Because hydrogen has an electron configuration of 1s1. So the hydrogens are 1 electron in an s orbital. And then you see that the carbon is surrounded by the 4 degenerate sp3 orbitals. They're all of equal energy. You could write sp3 on all of them if you want. The book doesn't do that. There's an exercise that you can do. If you take 4 balloons and you blow them up in equal size and you tie them together, they will spontaneously adopt a tetrahedral shape. So again, we know that a sigma bond is made from the sharing of 2 electrons, isn't it? This is a sigma bond, this is a sigma bond, this is a sigma bond, and this is a sigma bond. Each one of these 4 bonds, okay, is the sharing of 2 electrons. Well, where do those 2 electrons come from? We get 1 electron from the hydrogen and 1 electron from the carbon for each one of those bonds. And so you should be able to understand and be able to recognize sp3, sp2, and sp hybridization when you see it. This is something that you would have learned in general chemistry. Again, this is a review of general chemistry. You should also understand the relationship between hybridization and bond length and bond strength, which can be summarized quite simply, and we will look at that in a few minutes. But before we do that, I want to talk about an sp2 hybridization. If we take a look at the molecule ethylene that is shown here, and I can just draw it for you over here as well. So ethylene is C2H4, but what do we notice that's very different about ethylene when we compare it to methane is that it's got a double bond in it, doesn't it? Well, whenever we have two bonds between two atoms, the first bond is always a sigma bond, and the second bond is a pi bond, okay? So you need to understand the difference between a sigma bond and a pi bond. Now, it says here that each carbon in ethylene has to bond to 3 other atoms, right? If I look at this carbon, it's bound to 1, 2, 3 atoms. So that means it's got to have 3 unpaired electrons in degenerate orbitals, and then it's going to have 1 unhybridized electron, or an electron in 1 unhybridized orbital in order to make what? To make that pi bond. So we're going to do the exact same exercise again. Here is nothing more than the electron configuration of carbon showing the valence electrons. If we mix 3 of the orbitals so that we get 3 degenerate orbitals instead of 4 degenerate orbitals, these are called sp2. Why? Because we're combining 1 s and only 2 of the p orbitals. So we get an sp2. And we're going to leave one of the electrons in the 2p orbital, which is not hybridized. So that is a non-hybridized orbital. And so that explains why this carbon right here, and this one as well, those would adopt a trigonal planar molecular geometry, right? The bond angles are around 120 degrees. You can see they're close to that, right? They're around the neighborhood of 120 degrees. If you just said 120 degrees, that's perfectly fine, okay? And so, again, that explains why this carbon, both of these carbons, are sp2 hybridized. They form 3 bonds, sigma bonds, that are spread out equally, and they form 1 pi bond. Remember, a pi bond is always formed from an unhybridized orbital. If we take a look at what the sp2 hybridized carbon atom looks like, this is exactly what it looks like. You can see that we have 1, 2, 3 sp2, right? These are already labeled, but I'll label them again. These are all sp2 orbitals, right? And remember, we said that we had 1, 2, 3 sp2 orbitals. They each have an electron unpaired, and then we have the 2p orbital with 1 electron. Well, remember, a p orbital looks like this, so that explains why we have this here. That is the p orbital that is unhybridized. We could put here p orbital, and that is the one that's going to form the pi bond. Remember that the shape of an sp2 orbital results from having 33% s character and 2/3 p character, but we still draw it looking the exact same as the sp3 orbital. Okay, so we're not going to try to split hairs here and try to differentiate between sp2 and sp3 just by our drawing. We will label it, okay? All right, so if you have your microphone on, if you could turn it off, I would appreciate that. Somebody has their microphone on right now. So if we look at the model of ethylene, this is an orbital overlap diagram of ethylene. So what you're looking at is this molecule, right? This is the molecule that was on the last slide. This is just nothing more than ethylene. And now we have the 2 carbons. We have a carbon here. We have a carbon here, okay? So what they're doing is they're taking this carbon. This is a carbon right here. And what we're doing is we're putting 2 of them together. What's going to happen is 2 of the sp2 orbitals are going to overlap to form a sigma bond, right? This is an sp2, and this is an sp2. So that's our sigma bond. The 2 p orbitals, there's 1 here, and there's 1 here. You should know that a pi bond is formed by the overlap of p orbitals. Now, it's kind of hard to represent it properly, which is where it would actually show them touching like this. This is more of an artist's rendition, right? But the lines that I just drew here in black, maybe I'll highlight them in yellow. This is just to kind of show you that those orbitals are actually touching each other. Okay, so that's our pi bond. And then you see that we have sp2 orbitals over here, right? And they're overlapping with the 1s orbitals from each of the hydrogens. And so we have a total of 1, 2, 3, 4, 5 sigma bonds, and we have 1 pi bond, right? This is the pi bond. Now, don't get confused. Just because I put a line here and a line here, it doesn't mean it's a triple bond, okay? When you have the overlapping of 2 p orbitals like this, that is a pi bond, okay? 1 pi bond, but it overlaps in 2 spots, okay? But it's still just 1 bond, all right? So the p orbitals, again, overlap to form a pi bond. Well, let's move on from there. The pi bond, again, this is coming straight from our textbook, showing you what a pi bond is. It's the side-to-side overlap of p orbitals, and the electron density in the pi bond is spread out above and below the plane of the molecule like this. What's important is that you understand that pi bonds are actually weaker than sigma bonds. It might be a knee-jerk reaction to think, well, come on, Mr. Dion, there's more overlap. You got 2 spots where it's overlapping. Yes, but the overlap is still weaker, okay? Or it's a weaker interaction. And so a pi bond is weaker than a sigma bond. Well, let's look at a practice problem here. It says, consider the structure of formaldehyde. Identify the types of bonds that form the carbon-oxygen double bond. Identify the atomic orbitals that form each carbon-hydrogen bond. And what type of atomic orbitals do the lone pairs occupy? A lot to unpack here. Well, what's the molecule formaldehyde? Well, formaldehyde looks like this. So we have a carbon with a double bond to oxygen, and then we have 2 bonds to hydrogen like this. Now, what did we see earlier today? We saw that when carbon has 3 sigma bonds and 1 pi bond, it is sp2 hybridized, right? How do I know that that carbon is sp2 hybridized? And again, I'm repeating myself. It's because this is a sigma bond, this is a sigma bond, and this is a sigma bond. There is 1 pi bond, okay? Now, there's always somebody who asks me, does it matter? Could you label either side as sigma or pi? It doesn't matter. You could call this one sigma, this one pi. But whenever you have a double bond, one of the lines represents a sigma and one of the lines represents a pi bond. So we know that when carbon has 3 sigma bonds and 1 pi bond, it is sp2 hybridized. And so the answer to A, I'll just write it over here, is that there's 1 sigma bond in the double bond, and there is 1 pi bond in the double bond. So we have 1 of each. It says, identify the atomic orbitals that form each carbon-hydrogen bond. Well, we know that in B, the carbon and hydrogen, if it's just a sigma bond, that the orbital that's coming from the carbon is going to be the sp2 orbital, and that's going to be overlapping with the hydrogen 1s orbital. So the overlap is between an sp2 and a 1s of the hydrogen. And in C, it says, what type of atomic orbitals do the lone pairs occupy? Well, this one might take us a little bit more time, but let's look at the electron configuration of oxygen. Remember, valence electrons are the only electrons that are involved in bonding. But let's just look at the entire electron configuration, 1s2, 2s2, 2p4. So that is the electron configuration of oxygen. If we just look at the orbitals that contain the valence electrons, maybe I'll do it over here. We have 2s, okay, and then we have 1, 2, 3p. So we have 2p here. So we have 2 electrons in the s, and then we have 1, 2, 3, 4 electrons in the 2p. Well, if the oxygen has 2 lone pairs and 1 sigma bond, and it also has 1 pi bond, that means I'm going to have an electron in an unhybridized orbital, won't I? Right? I'm going to have 1 electron in an unhybridized orbital in order to make the pi bond between the oxygen and the carbon. So what we're going to do is we're going to hybridize, and then we're going to mix 1 of the s orbital, or the 1s orbital, sorry, with 2 of the p orbitals to make 3 degenerate sp2 orbitals, and we're going to leave the 1 of the 2p orbitals alone, aren't we? So that we can have 1 electron in there for the pi bond. Now remember, we have a total of 1, 2, 3, 4, 5, 6 valence electrons. Let's put them in. We have 1, 2, 3, 4, 5, and 6. Well, looky, everything has worked out perfectly, hasn't it? Because the oxygen and I'll just draw it in black here, the oxygen is surrounded by what? 1, 2, 3 degenerate sp2 orbitals. Okay, we got 3 degenerate sp2 orbitals. Look at this. In 2 of them, you have a pair of electrons. Well, that would be the lone pairs, right? And then in 1 of them, you have an unpaired electron. That is the electron that's going to overlap to form the sigma bond to the carbon, isn't it? Right? I have my carbon down here. We already agreed that the carbon was sp2 hybridized, so it's got 1, 2, 3 sp2 hybrid orbitals, right? Each one of the carbons has 1, 2, 3, like that. Okay, and then we have the 1s orbitals from the hydrogen. So this is our hydrogen, hydrogen. So they each have an electron. So there are all the sigma bonds, and there are also the lone pairs. Now the pi bond I haven't drawn, and I'll do my best to draw it in for you. I'll draw it in blue. So the pi bond means we're going to have an unhybridized 2p orbital here with an unpaired electron. And then in the carbon, we also have an unhybridized 2p orbital here. Again, this is Mr. Dion's best drawing here. And we know that those are going to connect like that to make our pi bond. And if you're like, what the heck did you just draw? It looks like a bunch of, funny shapes around the letter C and the letter O. What I just drew is this, okay? That's an orbital overlap diagram of formaldehyde. So the type of orbitals that the lone pairs occupy are sp2 hybridized orbitals. Let's move on. What about acetylene? We know that carbon can form a triple bond, right? That's one of the reasons why there are so many organic compounds, because carbon can bond to itself. It can form single bonds, double bonds, triple bonds. Well, if I have acetylene, which is shown here, how does carbon have 2 degenerate orbitals so that it can adopt a linear geometry, molecular geometry? You should know that the bond angle here is 180 degrees. Well, again, going right back to basics, if we look at the electron configuration of carbon and we hybridize 2 orbitals, then we're going to get 2 degenerate sp orbitals, and we're going to have 2 unpaired electrons in 2p orbitals. Why would I need 2 electrons in unhybridized orbitals? The reason why is because I have 1, 2 pi bonds, right? This is pi bonds, plural, right? And I only have 1 sigma bond, okay? And then, of course, the sigma bond between, that's not a sigma, is it? The sigma between the carbon and the hydrogen, okay? So if we look at the orbital overlap diagram, now I could just draw you the carbon itself. It would look something like this, where you have the carbon, you're going to have an sp hybridized orbital, you're going to have another sp hybridized orbital. They're going to get as far away from each other as possible. They will each have 1 unpaired electron, and then I'm going to have 2p orbitals. You're going to have 1 going up like this. This is a 2p orbital, and then you'll have 1 going in the back, kind of out of the plane like this, and then you'll have another one coming out in front like that. Anyhow, so what they've done in this next picture is they've taken 2 of these, what I just drew, and they showed them connecting to form the acetylene molecule. So again, if you're curious, if you're not 100% following me here, if you're like, what is this? What is this that's drawn here? This is an orbital overlap diagram of this molecule, acetylene. This is showing carbon with a sigma bond, right? That's this bond, right? We have this sigma bond here, right? We have a sigma bond here, and then we have 1 pi bond, and then we have the second pi bond here. So that explains the bonding in acetylene. All right, so let's take a look at another practice problem. This is practice problem 1.25. It says that nematine is a compound first isolated from the fungi Poria tenuis and Poria corticola in the 1940s and was shown to possess potent antibacterial activity. However, its structure wasn't verified until it was made in the laboratory much more recently. There's a typo here. There shouldn't be the number 7. It says determine the hybridization state of each carbon in nematine. Well, let me summarize what we just learned. We know that when a carbon, okay, if we're talking about carbon, when it has 4 sigma bonds, okay, then it is going to be sp3 hybridized. When a carbon has 3 sigma bonds, okay, and 1 pi bond, Okay, when we have that, we know that it's sp2 hybridized. And when the carbon has 2 sigma bonds and 2 pi bonds, when we have that arrangement, we know that it's sp hybridized. So let's start by looking at this carbon right here. Could anybody tell me what the hybridization of this carbon that I just drew the arrow to would be?
SP.
Absolutely. This is an sp hybridized carbon, right? It's got 1, 2 sigma bonds, and it's got 2 pi bonds. Other sp hybridized carbons would be, this is an sp hybridized carbon, this is an sp hybridized carbon. Let me see here. This is an sp hybridized carbon. Are there any others? I don't see any others right now. Anyhow, if I was to circle, oh no, there's another one here that I missed. Yep. That's an sp hybridized carbon. What about if I circled this one here in blue? Could anybody tell me what the hybridization of that carbon is? Yeah, I see somebody said sp2 in the chat, and they're 100% correct. That's sp2 hybridized, as is this one and this one. Okay, are there any sp3 hybridized carbons in this molecule? Absolutely there are, absolutely, right? This is an sp3 hybridized carbon. It's got 4 sigma bonds. This is sp3 hybridized, and this one is sp3 hybridized. So just by looking at the types of bonds on a carbon, we can identify the state of hybridization very quickly. And if you're like, why did you go over all that electron configuration stuff, Mr. Dion? It's because it's important that you understand how bonds are formed. We don't want to just look at bonds blindly and not have any knowledge of how they are formed, because bonds tell us a lot about a molecule's reactivity. If we understand, that a pi bond is weaker than a sigma bond, then we can make some inference later on in the class as to, where a molecule might react. Okay, so that's the kind of thought you want to have in organic chemistry. Well, if we look at this slide here, it asks us to simply rationalize the bond strengths and bond lengths below. Let's start by looking at the bond lengths. We'll look at that first. And you see that when we go from a single bond to a double bond to a triple bond, that the bond length decreases, doesn't it? We go from 1.54 angstroms to 1.34 and to 1.20. And so the conclusion that we would draw here is that the more bonds there are between two carbons, the shorter the bond length will be. We could write that down. More bonds equals shorter bond length. Okay, the more bonds we have, the shorter the length. And the reason why is simply because the carbon atoms have to get closer and closer together as there is more orbital overlap. Okay, it also asks us about bond strength. So if we want to address the bond strength, that would be summarized by the bond energy. And you can see that as we go from a single to a double to a triple, that the strengths of the bonds increase. And that is hopefully intuitive to you, that the more bonds we have, the stronger the interaction is going to be between the two atoms. So more bonds, okay, equals stronger, okay, stronger bond. All right. I'm not sure exactly what you mean by a rule of thumb. A rule of thumb. Well, we're going to look more at hybridization in just a second here. So just give me a few minutes and we'll talk even more about hybridization of elements like nitrogen and oxygen. All right, so let's take a look at a practice problem. This is question 1.26 from our book. It says rank the indicated bonds in terms of increasing bond length. So if I was to label these 1, 2, 3 like this, and if I was to put longest to shortest, who could tell me which one of these is going to be the longest bond? Would it be 1, 2, or 3?
3 for 1.
1 is going to be the longest, right? 3 is going to be the shortest because it has the most bonds. And then 2 will be intermediate because the more bonds that we have, the shorter the bond is. Now, if we were to rank these, what if we were to rank so this is length. So this is length. And what if we were to rank them in terms of strength? It doesn't ask us to do that, but let's do it. This is a question that was on an ACS final one year. If we were to rank these in terms of strength from strongest to weakest, which one of these is going to be the strongest bond?
3.
Yeah, 3. And 1 is going to be the weakest, and 2 will be somewhere in the middle. So it's imperative that you understand the relationship between number of bonds and bond strength and bond length. All right, let's talk about molecular geometry. One of my favorite subjects in general chemistry is VSEPR theory, valence shell electron pair repulsion theory, which is nothing more than, quit crowding me, bro. It's just that electrons don't like each other. They want to repel each other because electrons are negatively charged. So they seek to get away from each other as far as possible. Well, it says here that valence electrons are, again, going to repel each other, whether they're shared or whether they're lone pairs. And if we want to determine molecular geometry, an easy way to do that is to start with what's called the steric number, And the steric number is nothing more than the sum of the number of sigma bonds and the number of lone pairs. So we could write that down here. So number of lone pairs plus number of sigma bonds. We tally those up. So if you look at the carbon in methane, the nitrogen in ammonia, or the oxygen in water, you can see that they have different numbers of bonds and lone pairs, or sigma bonds and lone pairs, but they all have the same steric number. So that tells you that all of these bonds and lone pairs are always going to adopt a tetrahedral arrangement, because when we have 4 pairs of electrons, what's the farthest they can get away from each other is to adopt a tetrahedral arrangement. So here's the answer to the question that was in the chat. It says here the steric number can translate to the hybridization of the central atom. So here's a really quick and dirty summary. This will answer your question very quickly. If the steric number is 4, it's sp3 hybridized. If the atom has a steric number of 3, it's sp2. And if the atom has a steric number of 2, then it's sp hybridized. Nothing more than that. So you can see that each one of the atoms, the carbon and the nitrogen and the oxygen, and all of these molecules, all are sp3 hybridized, aren't they? Because they all have a steric number of 4. Sometimes I'll allude to steric number, throughout the class. And for steric number, I usually use the abbreviation SN, because let's face it, I can't spend that kind of time writing out steric and number. Well, we know that all of these molecules have the same steric number, so the electrons pairs, whether they're sigma bonds or lone pairs, are all going to seek to get as far away from each other as possible. But their molecular geometries are different, aren't they? If we examine those 3 molecules, you should know that they have different molecular geometry. So it says for any sp3 hybridized atom, the 4 valence electron pairs will form a tetrahedral, what is the next word? Electron group geometry. Okay, so it's very, you have to be very careful with the wording here. So another way of another way of saying this is saying the electron geometry is tetrahedral, right? In methane, the 4 bonds are all spread out as far away from each other as possible. In ammonia, the 3 bonds in the lone pair are all spread out as far away from each other. The same thing occurs in water, but their molecular geometries are different, aren't they? These 3 molecules have different molecular geometries. Now, I've already gone over the molecular geometry of the methane molecule, and we know that this is tetrahedral. I'm just going to throw this out there to my students. Who read the textbook or who reviewed their general chemistry and can tell me what the molecular geometry of ammonia is?
The trigonal pyramidal?
Yeah, it's trigonal pyramidal. Yeah, trigonal pyramidal. All right, that's perfect. And who could tell me what the molecular geometry of water is? Not the electron geometry, the molecular geometry.
Bent.
Bent.
Exactly, it's bent. Because molecular geometry only considers bonds. So bonds only, okay? Whereas electron group geometry considers bonds, not bonds, bonds, and lone pairs. It considers both. Look, I can't stress this enough. You've got to know the difference, that molecular geometry considers only the bonds, and that electron group geometry or electron geometry considers bonds and lone pairs. Well, I've got a summary table coming up here, and this comes directly from your textbook. Again, if you look at methane, it's got 4 bonds, 0 lone pairs, steric number of 4. The electron geometry, and that's what this is here. This is electron geometry. here they're calling it something fancy, the predicted arrangement of electron pairs, okay? So you see that it's tetrahedral. Again, ammonia and water both have a tetrahedral electron geometry, but they're molecular. So this says predicted molecular geometry. I guess I could just put a box around their molecular geometries are all different, aren't they? Right? Tetrahedral, trigonal pyramidal, and bent. You can see that boron trifluoride is trigonal planar because it's got 3 bonds and no lone pairs. I could draw the Lewis structure of boron trifluoride for you. Okay, this is one you definitely would have seen in general chemistry. And the next one is beryllium hydride, BeH2. I could draw that down here. It looks like this. Beryllium's an interesting element in that it only forms 2 sigma bonds. Anyhow, so it's got a steric number of 2. Its electron geometry of BeH2 is linear, and its molecular geometry is linear. Again, this should be a review of your general chemistry. So again, a little bit more help with respect to steric numbers and hybridization. A student had a question in the chat about hybridization. If you've got a steric number of 4, 3, or 2, the hybridization is sp3, sp2, and sp respectively. From the hybridization, you can tell the electron geometry right away, right? All of these green boxes represent the electron geometry. But remember that electron geometry considers sigma bonds and lone pairs, whereas molecular geometry, and that's what's shown down here, this is molecular geometry, considers bonds only. And something that I forgot to say on the last slide, I'm sure that most of you know this, but I just want to be doubly sure with you. When I say bonds, I mean the sigma bonds only, okay? So sigma bonds only, sigma bonds and lone pairs, okay? We don't take pi bonds into account when we are evaluating molecular geometry. Of course you can, but it's not necessary. Anyhow, and down here we have the models, the space-filling models, or ball and stick models. This is methane down here. This is ammonia here. This is water. This is boron trifluoride. And this is beryllium hydride here. All right, some good review of molecular geometry. All right, well, with that in mind, let's take a look at a practice problem. This is question 1.27 from our textbook. It asks us to use valence shell electron pair repulsion theory to predict the geometry for each of the following structures. We've got BH4 with a negative charge on the boron, and then we have BF3. Well, we already went over BF3 on the last slide, so I'll just kind of draw in the lone pairs. You know, I have a saying, friends don't let friends leave lone pairs out, right? You should always include lone pairs in your Lewis structure. But you can see, let me just ask you guys, could somebody tell me what the steric number of the boron is, the central atom? Not a trick question. Mr. Dion is not into trick questions. Oh, the
3.
steric. Yeah, absolutely, right? Because the boron only has 3 sigma bonds, right? It's got 3 sigma bonds, okay, and 0 lone pairs. Therefore, the steric number is equal to 3. If we back up here, we know that when the steric number is 3, what's the hybridization of that boron? We know that it's sp2 right away. So the hybridization is sp2. I mean, it's not asking for it, but let's write it down, okay? Now, if the steric number is 3, we've got 3 sigma bonds and lone pairs. Let's go back to this table here, which you need to know, okay? When you've got no lone pairs in your sp2 hybridized, you are trigonal planar, my friend. So there we go. We can write that down as well. We can say that this molecule is trigonal planar. All right, well, with that in mind, let's take a look at the other one, A. Could anybody tell me what the steric number of the boron here is? Again, not a trick question. Yeah, thanks, Autumn. It's 4. Yeah, the steric number is 4. If we back up, okay, we see that when the steric number is 4, it's sp3 hybridized. It's got no lone pairs. It is tetrahedral, just like that. So you need to have that entire table in your brain, okay? So we know that this boron is tetrahedral, and that it is sp3 hybridized. Look at that. Very quick. We can make a lot or get a lot of information about a central atom, okay? Just by looking at the number of sigma bonds and the number of lone pairs, determining the steric number. So again, you would want to have this entire table in your head when you step into the quiz room on Monday. That's one of the things you'd want to know. Molecular polarity and dipoles, right? Well, I can tell you right now that we're not going to do any calculations with respect to dipoles. And the book goes into a little bit of detail about calculating, dipoles and things like that. But all you need to know for Chemistry 3101 is to have an understanding of what is a polar bond and what a dipole moment is. So let's review what it says on this slide. It says that electronegativity differences result in a bond that is polar. Induction, or the shifting of electrons within an orbital, results in a dipole moment. Let's say, for example, we looked at a bond between carbon and fluorine. That's a totally reasonable bond. Well, we know that carbon has an electronegativity of 2.5 and fluorine has an electronegativity of 4.0. Therefore, the difference in electronegativity is going to be 4 minus 2.5. That's 1.5. And that falls in the region of a polar covalent bond. So this would be a polar bond. Now, since the fluorine is more electronegative, we can represent that dipole moment using these little delta pluses and delta minus. Now, again, since the fluorine is more electronegative, we would put a delta minus and we would put a delta plus by the fluorine. Another option to represent a dipole moment is to use a vector. So you could also use a vector like this and put the arrow towards the more electronegative element, and then you put a little cross down by the one that is less electronegative. So a dipole moment is equal to the amount of partial charge times the distance and the charges that are separated. Again, I'm never going to ask you to use this formula. Okay, you'll never be asked to use this, not once. You can take that one to the bank. Okay, I'm never going to ask you to calculate anything in Dubai. I would recommend reading that section, but you will not be asked to measure a dipole. You will qualitatively be asked to assess dipoles. So you should be able to look at a molecule and say, hey, this is a polar molecule, this is a nonpolar molecule. I've taught general chemistry the last 3 semesters at UCCS, so I know that we teach our students this, to be able to look at a molecule and assess whether or not the molecule is polar. Let's take a look at this molecule right here on the top left. This is CH2Cl2. This is dichloromethane. Somebody took the time to put down the molecular geometry. You can see that it's tetrahedral. You see that this carbon is sp3 hybridized. But remember, a carbon-hydrogen bond isn't really a polar bond. It falls below the range of being a polar bond. The difference in electronegativity between carbon and hydrogen is only 0.4, and the cutoff is around 0.5. But we do have a dipole being shown between the carbon and the chlorine. That's around 0.5, okay? So we have those two vectors. But what happens when we add or we sum those two vectors, right? If you have a vector pulling this way and a vector pulling that way, well, the net result is that it's going to pull in this direction. So you should know how to add vectors together in your mind, if you will. Okay, so overall, this is a polar molecule. So that means that dichloromethane is a polar molecule. If we look at ammonia, excuse me, you can see the dipoles between the hydrogen and the nitrogen, because nitrogen is more electronegative than hydrogen. You can see the dipole from the nitrogen to the lone pair. We always draw a little dipole towards the lone pair because they're unpaired electrons. So anyhow, so if you tally up all 4 of those vectors, you're going to get a net dipole moment going what? Straight up like this, like a rocket, like this one right here. So ammonia is a polar molecule, and the same thing applies to water. Give me a thumbs up if you follow me on a polar molecule, even if you're the kind of person who's like, I have to review it, but I did learn it. Okay, I do know what polarity is. It's very important that you understand when a molecule is polar and when it is non-polar. Is anybody with me? Okay, great. Sarah, thanks. All right, Abigail, I got a couple of people who are with me on, what is a polar molecule? What is a non-polar molecule? Very important that you're able to look at a molecule and assess its polarity qualitatively. Something you'll see, where is it here? Okay, this is another, sorry, I was one slide ahead of my notes here. Anyhow, this slide here just says, it's kind of a reminder that you have to know a molecule's molecular geometry before analyzing its polarity, don't you? Okay, if you don't draw your molecules correctly, you're not going to be able to assess polarity. Impossible. Okay, so that means you have to have a complete understanding of molecular geometry before you start assessing polarity. All right. The question that's asked down here is kind of a funny one. I added this here. It says, would water have a different dipole if it was linear? Right. If you were to draw water, so here's water. We know that water is bent. One of my students told me earlier, he said, water has a bent molecular geometry. If water was linear, okay, water is not linear, but if it was, then you'd have a dipole going this way and you'd have a dipole going that way, okay? Then they would cancel out. It would be nonpolar. And so we would have serious problems. In fact, the life that we know would not exist. So you really have to understand molecular geometry. Anyhow, just kind of a helper here. This is what I wanted to get to, was what's called an electrostatic potential map, or an EPM. I'm never going to ask you to draw an electrostatic potential map or anything like that, but they are used throughout the textbook and they are helpful for students, okay, to really look at a molecule. If you look at this molecule here, this is chloromethane, and you look at it and say, well, where's the electron density? If you look at an electrostatic potential map, I kind of lost myself, didn't I? Here, where was I? Find it. Yeah, I was right here. Anyhow, you look at the electrostatic potential map, where it's red, okay, wherever it's red, maybe I should use the color red, okay? That means that you have high electron density. And wherever it's blue, okay, that's where you have low electron density. Anyhow, again, it's used throughout the textbook. I think it's really handy. I will use it from time to time in the textbook, or sorry, in my notes, more so when we get into mechanisms and understanding how reactions work. Okay? Anyhow, let's talk a little bit more about polarity and dipoles quickly. If you look at these molecules, you can see here that the dipole moment can be quantified using the unit of debye, the letter D here. It's a unit that measures polarity. Again, I'm never going to ask you to calculate anything in debye, but you should know that the greater the dipole moment, so the higher this number, the more polar the molecule is. So if we were to compare, let's say, if we were to compare acetone and carbon tetrachloride, well, you can see that acetone is 2.69 debye and carbon tetrachloride is 0. So carbon tetrachloride is not polar whatsoever. Anyhow, just to understand the concept of a dipole moment. That's something that's very important. All right, let's look at question 1.31. I don't think I have time to go through all of these questions, but remember that the solutions are in your the solutions manual that you all have access to. You know what? I'm going to start with J, because in J they've gone ahead and they've drawn the molecular geometry for us of this molecule. This is called trans 1,2-dichloroethane. Anyhow, we'll worry about the nomenclature later on. But if you look at this molecule, can anybody tell me, are there any polar bonds in this molecule? Or that would be considered polar? Yeah, absolutely. Who could tell me which bonds are polar?
The carbon chlorine.
Yeah, we just saw that a couple slides ago, right? Remember we looked at CH2Cl2? Well, this molecule just has an extra carbon in it, doesn't it? So we know that the carbon chlorine bonds are polar. I'm going to maybe expand this a little bit. Anyhow, so I have one dipole going in this direction for the carbon chlorine bond, and I have another one going in this direction. Now, again, I'll just address this one more time. For the students who are like, well, there is a difference in electronegativity between carbon and hydrogen, Mr. Dion. Yes, there is, but it's so small that we don't consider it. Okay, it is there, it's small, and we don't consider it. So if I have two dipoles in this molecule and they're pulling in opposite directions like this, can anybody make a hypothesis or answer the question and tell me, would this molecule be polar, yes or no?
No, wouldn't they cancel each other out?
Absolutely.
Nope.
Not. So we'll put here not polar, and we'll just make it quick here. Dipoles starts with C, ends with ancel. That's right, they cancel. There you go. All right, let's look at the next one, D, which is CCl2Br2. So the carbon is going to have 4 sigma bonds because, as I told you, halogens in this class are always monovalent. They only ever have one bond. So I'm going to draw the structure of CCl2. I mean, there's a variety of ways that you could draw it like that. Anyhow, and I'll put the two bromines. I'll put one of them back here in my tetrahedron. I'll put in all my lone pairs. I'll put the other one here, like so. Okay. Anyhow, you know, if you look at the electronegativities of chlorine and bromine, I'll help you out here in case you don't have them memorized. Chlorine is 3.0. Bromine is 2.8. It's kind of a funny question. Anyhow, if you look at the dipoles, yes, I mean, we just discussed that, yes, the bonds between the carbon and the chlorine are polar. But you know what? There's a little tug from the bromine too. You know, it's kind of pulling in this direction. Maybe I'll make the arrow smaller because it is slightly smaller. So I'll make it like this. So if you tally up those four vectors, since these two are bigger, there is going to be a net dipole in this direction. Okay, there will be, this is the net dipole, so it is polar, but I'd say it's slightly polar, slightly polar. So is it polar? The answer would be yeah, but it doesn't have a big dipole. Now, somebody might be asking, well, come on, Mr. Dion, how come you didn't evaluate the polarity here? Because you're considering a really small one here. Look, I could have done it in that problem, and let me prove it to you. If I was to draw the dipoles here, right, you can see that those two dipoles are going in equal and opposite directions. So those are going to cancel. So the molecule is still non-polar. In fact, I don't know why I wrote not polar. Why didn't I write non-polar? That's better. Okay, anyhow, so slightly polar. And the one on the top, this is dimethyl ether, which I think I might have mentioned to you earlier on in the class. Anyhow, dimethyl ether, I'll just help you out with this one quickly. But if you have the two carbons attached to an oxygen, right, that means that the oxygen is going to have the two bonds and it's going to have two lone pairs, won't it? So we have C. Let me do this like this. The CH3, I'm just going to draw those condensed. Those carbons are tetrahedral, but I'll draw that condensed because we know that the carbon-hydrogen bond is nonpolar. So that means the oxygen is bent, just like in water. We have a dipole going in this direction, and we have a dipole going in that direction. So what do you think? Is dimethyl ether polar, yes or no? If it's bent and it's got two vectors going in that direction. Oh, the answer be yes or no.
Wouldn't they cancel each other out, so it'd be nonpolar?
No, they don't cancel each other out because they're not heading to each other straight on, right? They're not colliding straight on. The only way they can cancel is if they're pulling in equal and opposite directions or if they're pointing towards each other, right? In the exact same orientation. Think about it. If you have a car, if you have two cars colliding with equal mass, right, and they make a big impact in an intersection, if they're hitting each other head on, are they going to move anywhere? No, they're going to stop dead in their tracks. Right? But if you have two cars, one flies in from this direction and one flies in from this direction, when they collide, what's going to happen? Okay. Overall, there's going to be some momentum pulling in this direction. So you're going to have a net vector going in that direction. And so the net vector for dimethyl ether is going to be in this direction, right? When you tally those up. So this is going to be a polar molecule. All right. Well, let's move on from there. And let's talk about intermolecular forces. Again, I told you I would give you an introduction or introduce myself a little more later on, probably in the second chapter of the class. But anyhow, for those of you who have never had me as an instructor before, I haven't taught chemistry, you know, my whole adult life. I actually spent almost 20 years as a medicinal chemist in the pharmaceutical industry. So I basically spent my entire life working in the lab doing research, and I even discovered a drug. And I've been a teacher since I immigrated to the United States a number of years ago. But if I could summarize the job of a chemistry teacher on the planet Earth, you know, I tell everybody that my job nowadays is I wake up in the morning, I brush my teeth, and I talk about intermolecular forces, or IMFs, until I go to bed. That's what it's like to be a chemistry teacher. And I'm kind of being facetious here, but the idea is that intermolecular forces are so crucial for your understanding of chemistry. Think about any subject that you've ever enjoyed in your life. Was it a subject that you were confused about the whole damn time? No, it was something that you understood. When you understand something, you enjoy it more. And so intermolecular forces are crucial for your understanding of physical properties, things like solubility, boiling points, density, state of matter, solid, liquid, or gas, melting points, etc. All of these are going to be affected by the attractions between separate molecules. Now, I've taught chemistry long enough to know that I can sit here and pontificate about intermolecular forces all day, but you will definitely have to read this section if you're still unsure about intermolecular forces after taking general chemistry. But you need to understand the difference between a dipole-dipole interaction or a dipole-dipole force, a hydrogen bond, and dispersion forces. And sometimes we call these London forces. You'll hear me say London forces a lot. London forces, again, sometimes we call those fleeting dipoles. Anyhow, you need to know these. In fact, I'll even write that, know these, okay? And well, make sure that you understand the differences between the types of intermolecular forces. Now, in general chemistry, I know that you learned more types of intermolecular forces, but these are the three that we're going to be concerned with in organic chemistry. So I'm going to go over these quickly. The first one, the dipole-dipole attraction, is the attraction that results between polar molecules. Here you have 3 molecules of acetone. So this molecule here, this is called acetone. It's nail polish remover. So if you look at the structure of acetone, and I'll draw a third molecule of acetone over here. It's CH3, and then we have a carbon with a double bond to an oxygen, and then we have another CH3 here. Now remember, we said that the carbon-hydrogen bond was nonpolar, so we don't have to worry about that. But we know that there is a polar bond between carbon and oxygen because oxygen has the silver metal. It's got an electronegativity of 3.5, and carbon is 2.5. Therefore, that is a polar bond. We could either draw the dipole like this, or we can represent it with these delta symbols. And I'm going to do that and put a delta minus by the oxygen because it is more electronegative. It is taking more of the electron density in these bonds right here, the sigma and the pi. And the carbon is more electropositive. Well, what do we know about opposite charges? Opposites attract. People who think alike stay together, but opposites attract. And so we have a delta minus on this molecule of acetone. What if there's another molecule of acetone next door? What part do you think this delta minus is going to interact with? Is it going to interact with the delta minus? Hell no. It would repel that. So it's going to be attracted to the carbon here. It's going to be attracted to the delta plus. And so when you have a molecule with a permanent dipole, they are going to be attracted by their delta pluses and delta minuses. It says here, the dipole-dipole attractions between acetone molecules increases acetone's boiling point and melting point, while similar molecules without a dipole are like isobutylene have lower boiling points and melting points. And if you're like, what the hell is isobutylene? Let me show you. Here are isobutylene and acetone. We just saw that acetone is polar, right? There's a dipole because the oxygen is delta minus, the carbon is delta plus. Now they just drew it with an arrow here. That's totally fine. Isobutylene only contains carbon and hydrogen. There is no dipole in this molecule. So even though they look similar, right, they have molecular weights that aren't that different, okay? Let's just compare one of their physical properties. Look at the boiling points. Acetone boils around 56 degrees Celsius, okay? So you have to heat it up in order to boil it. It's a liquid at room temperature. But look at isobutylene. What the heck? Its boiling point is below the freezing point of water. That means it's a gas at room temperature. It's vaporized at minus 5 degrees Celsius. It's a vapor. The reason why is because there's no delta plus, there's no delta minus, there's nothing to attract 2 molecules of isobutylene. Could anybody tell me what kind of intermolecular forces 2 molecules of isobutylene would experience? I'm testing you here. If you had a second molecule of isobutylene, there is an attraction between them, but can anybody tell me what type of attraction it would be?
London dispersion.
Absolutely. It would be a London dispersion force, right? Because we know that nonpolar molecules are attracted by London forces, or what we call a London dispersion force. Sorry, Mr. Dion's losing it here. Anyhow, a fleeting dipole. All right. So dispersion force or a London force. Anyhow, before we get into London forces, let's talk about hydrogen bonding. Hydrogen bonding, the only time you're going to see hydrogen bonding in chemistry class is when you have a bond between oxygen and hydrogen, nitrogen and hydrogen, or fluorine and hydrogen. Those are the only times you're going to have a hydrogen bond. Now, if you're like, What the heck is a hydrogen bond? Well, again, something you would have covered in general chemistry, but we'll review it. A hydrogen bond is nothing more than a very strong type of dipole. That's all it is. And if you're like, why couldn't they just call it a dipole? Because it's so much stronger than a regular dipole that it belongs in a class on its own. Now, it's important that you remember that a hydrogen bond is not a bond. It is not an actual bond. And if you're like, why do you do this kind of stuff in chemistry? I don't know. I didn't invent the name. I'm just teaching it, okay? The reason we call it a hydrogen bond is, again, because the intermolecular force is so much stronger than a dipole force or a London force, okay? So hydrogen bonds are, again, the result of delta plus and delta minuses. The only difference is the delta plus is big and the delta minus is big, okay? They're relatively large. So hydrogen bonding, if we look at the hydrogen bonding in water, for example, we know that hydrogen has an electronegativity of 2.1. Oxygen has an electronegativity of 3.5. That means that the delta En, and I'm doing this in my head, is 1.4, right? So there's a big difference in electronegativity. The delta minus here is big. And so the attraction between the delta plus on a hydrogen and the delta minus on a lone pair of a neighboring oxygen is strong, very strong. And we call that a hydrogen bond. We represent it with a dashed line between a hydrogen and a lone pair. So this is a lone pair. The same thing applies for ammonia. However, the electronegativity of nitrogen, again, hydrogen is 2.1, nitrogen is only 3.0. So the delta En here, delta En is 0.9. So the delta minus isn't quite as big here, is it? But again, we represent it the exact same way, a dashed line between the delta plus on the hydrogen and the delta minus of a lone pair on the nitrogen. So that's hydrogen bonding. Again, the only time we see hydrogen bonding, if you don't have any oxygens in your molecule, you do not have hydrogen bonding. If you don't have any nitrogens or fluorines, if you don't have one of those three elements, hydrogen bonding is impossible, as we say in French. It's impossible. Okay, let's take a look at another example here. Again, you've got to have ONF. You've got to have oxygen, nitrogen, or fluorine, okay? Because those atoms carry a large partial positive charge. The delta plus and the hydrogen can attract the large delta minus charges on the other molecule. So this is two molecules of ethanol, which is found in, additive in gasoline, alcoholic beverages, right? This is an ethanol molecule over here. Anyhow, you see an oxygen-hydrogen bond, and I see an oxygen-hydrogen bond here. So you can show a hydrogen bond, again, between the delta plus, so between the hydrogen and the lone pair of an oxygen, like that. All right. Now, again, remember, a hydrogen bond is not a covalent bond. It says even with these big partial charges, a hydrogen bond is still 20 times weaker than a covalent bond. Give me a thumbs up if you follow me on hydrogen bonding. You're like, hydrogen bonding, Mr. Leon, I was born to know about hydrogen bonding. I know, I've known this, ever since I took general chemistry. Intermolecular forces was my favorite part. You walk down the street, somebody, walks up to you, hey, could you explain hydrogen bonding to me? You're like, yes, I could. Something I say to my students is, and this doesn't really work during a pandemic, but I know that many of you have been students long enough at UCCS to know about the Science Center, and you can still go to the Science Center now. I just think that due to social distancing, you might not be able to do this. But what I used to tell my students is this, like I'd look at a student's name like Ross or Autumn or Courtney or Jonathan, and I'd say, you know what, you guys, you should be able to go to the Science Center today, okay? Go up to a first-year student, some poor first-year student who's totally lost, and all of you who are hearing the sound of my voice, everybody who's in 3101 should be able to go to a first-year student and say, let me explain intermolecular forces to you, okay? You're stuck, I can explain it. I'm in organic chemistry, I know what I'm talking about, okay? You're like general chemistry, been there, done that. It's not my first rodeo. Anyhow, the whole thing about protic and aprotic solvents, it says here that solvents that we use, so things that we use to run reactions in, or liquids that we use to run reactions in organic chemistry, if they have the capability to do hydrogen bonding, we call those protic solvents. And if they don't have a capability to do hydrogen bonding, we call them aprotic, right? So since acetic acid, which is one of the main components in vinegar, Since it has an oxygen-hydrogen bond, it's considered protic, right? Whereas if you look at diethyl ether, it's got an oxygen, but there's no oxygen-hydrogen bond. If you look at dimethyl sulfoxide, it's got an oxygen, but it doesn't have any hydrogen. Dimethyl sulfoxide, it absorbs through the skin really quickly. And if you've ever had cold canned corn, and you're like, what? Yes, if you've ever eaten canned corn just without warming it up, you get that taste in your mouth when you spill dimethyl sulfoxide on your skin. So I wouldn't recommend it. All right, let's move on. We could talk about those all day, but let's talk a little bit more about hydrogen bonding. Look at this. Look at these three compounds here, okay? We're going to do a whole chapter on amines in Chemistry 3111. But if you look at these three compounds, this is called trimethylamine, this is ethylmethylamine, this is propylamine. All three of these compounds have the same molecular formula. All three are C3H9N. So they all have the same molecular formula, but they all have really different boiling points, don't they? Yeah, absolutely they do. If you look at ethylmethylamine and propylamine, why do you think that those two have much higher boiling points than lowly old trimethylamine? Can anybody explain that to me? Why do those two have such high boiling points?
Isn't it the hydrogen bonding?
That's exactly right, because they're capable of forming hydrogen bonds, aren't they? Because this one, sorry, I need a highlighter. Ethylmethylamine has one nitrogen-hydrogen bond, and this one, propylamine, has two, right? So these two molecules are capable of H bonding, right? We have a nitrogen, but there's no nitrogen-hydrogen bond, is there? So there's no hydrogen bonding in trimethylamine. And so the intermolecular forces between two molecules of trimethylamine is going to be much lower than those of these two molecules. Now I got one more question for you. Could anybody, I'll ask Byron. Byron, could you explain the difference? Or I'm just teasing. It could be anybody. Could somebody explain the difference between these two? Why would propylamine have a higher boiling point? I mean, come on, it's 12 degrees higher than ethylmethylamine. Could anybody explain?
Because they have two hydrogen points versus one.
Damn right. Yeah, pardon my language. Couldn't have said it better myself, right? So here we have the possibility of two H bonds, right? And over here we only have one. So that's the rationale there. Anyhow, just some food for thought. All right, let's move on and talk about hydrogen bonding. I know that many of you are biology majors. I can see what your major is on the class list. And you should know that the alpha helix in DNA is held together by hydrogen bonds. Hydrogen bonds are also found in enzymes and proteins. If any of you have studied primary, secondary, tertiary, and quaternary structure of a protein, you would know that secondary, tertiary, and quaternary all involve hydrogen bonding to some degree. And let's move on to the most elusive of all of the intermolecular forces, the elusive London force. London forces, for some reason, seem to be the most difficult for students to understand. But if you have two molecules that are nonpolar, right, zero Debye, if they're nonpolar molecules, they still have a small attractive force between them. And we call that a transient or a fleeting dipole or a momentary dipole, or as one of my students called it, the London force, right? The London dispersion force, right? Now, what the heck is a London dispersion force? Let me explain it to you quickly. It says nonpolar molecules normally have all of the electrons. They're spread out evenly around the molecule. Everything's perfectly even. But what do we know? Let me tell you something right now to remember for the rest of your life. Don't get a tattoo of this, but remember this for the rest of your life. Electrons, if they can move, my friend, they will. Electrons are very high energy. They're like hyperactive children. If you let them move, they are going to move. So with that in mind, if we look at a big old molecule, now the molecule that's shown here is pentane. And again, you don't need to know exactly what pentane is quite yet, but you see that you have CH3, CH2, 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 and CH3. Now, what if all of the electrons in pentane are all spread out evenly? Well, then there's not going to be any interaction between that pentane and another molecule. But here's where it gets interesting. I told you that electrons can move, right? Or like to move. And if they can, they will. What if at one moment in time, let's go back. Do you see this word, transient? Did you hear me say the word fleeting? fleeting means what? If you said we had a fleeting relationship, it wasn't a long-term thing, right? It was short, a fleeting relationship. So a fleeting dipole means this. What if, in a moment of time, most of the electrons move to one side of the molecule? It just happened spontaneously. It's not, they don't stay there. They're not like, let's just move here and stay here. But if it happens quickly, what's it going to do to the neighboring molecule? What kind of effect is it going to have? Well, we know that opposites attract, don't we? Okay, and like charges, what? They repel each other. So that means that all of the electrons on this molecule are going to be like, get me the hell out of here. Look at all these electrons over here. They're going to move over to this side of the molecule, and that's going to create a large delta plus over here. So then there's going to be an attraction. I didn't say, Mr. Dion didn't say it was going to be long, did he? He didn't say that those electrons are just going to camp out there forever and these molecules are going to be attracted to each other forever. No, I said it was short. I said it was quick. I said it was fleeting. I said it was weak because it happens very quickly. Okay? So
Damn, just like my exes.
there you go. To summarize, over here, it says such fleeting attractions are generally weak. Why? Because on paper, it looks like, man, Mr. Dion, those electrons are just staying there, man. They're not even moving. Well, I'm here to tell you that very quickly, these electrons move somewhere else, right? But the net result is that it did happen, right? I know it happened. So there is some attraction, okay? And the bottom line is this, like any weak attraction, if you have enough of them, they can add up to be significant. Think about Velcro. If you were to examine your sneakers right now, right? I'm assuming that everybody's wearing Velcro sneakers, okay? If you were to examine the Velcro on your sneakers or on your watch, okay? The little hook there on one part of the Velcro that holds the other part, if you were to take one of those and try to pull it apart, it doesn't take a lot of energy, does it? I have a 3-month-old baby at home. She could do it, okay? But let's say you had a piece of Velcro that's 1 mile long, and I said, hey, can you separate that for me? That would take you some effort, wouldn't it? Even though the force is weak, it still is going to take a lot of energy to break them apart if you have a lot of London forces, okay? So what does that mean? The conclusion would be the greater the surface area of a molecule, the more temporary attractions you could have, the more dipoles you're going to have, fleeting dipoles. So the bigger the nonpolar molecule, the stronger the attraction, the greater the intermolecular forces, the higher the boiling points, the melting points, et cetera, et cetera. You can read this thing about the gecko in your own time. I will not be asking you anything about insurance on the first quiz, but if you look at these 3 molecules, butane, pentane, and hexane, you see that all 3 of them are hydrocarbons. What does that mean? They're just made of carbon and hydrogen. So there is no polar bonds anywhere in here. But you see that the boiling points increase as the molecules get bigger. And it's because there's more opportunity for London forces, aren't there? Okay, still the same kind of force, but just because there's more surface area, we can have more London forces and therefore a stronger attraction. And if you're thinking, well, what about, Mr. Dion, what if I was to branch a compound, right? If you look at the 3 compounds on this page, all are C5H12. They all have the same molecular formula, but they have very different boiling points, don't they? And the reason why is because if you have branching in a molecule, it lowers the surface area, and therefore you're just not going to have as much interactions. Right here you have kind of a cylindrical shape. If you put 2 hot dogs next to each other, you can have all kinds of interaction between the long side of a hot dog. If you put 2, rubber balls to each other, well, there's not going to be much interaction in a molecule that's got a spherical shape. All right. So in the interest of time, I'm just going to talk about solubility here very quickly because we only have 4 minutes left. But you should know the rule, the general rule, that like dissolves like. So that means a polar compound is going to mix generally well with another polar compound, and a nonpolar compound is generally going to mix well with another nonpolar compound. And the 2, generally speaking, don't mix. So if you try to mix a polar and a nonpolar compound, they're not going to mix. And that's why oil and water don't mix well. Anyhow, solubility, if you think about, not our dirty cloths, shouldn't it be our dirty clothes? Anyhow, Mr. Dion needs to learn how to spell. Anyhow, if you think about, dirt and grease, if you want to wash away dirt and grease, you wash it away with a soap. Well, a soap is nothing more than a fatty acid that's been hydrolyzed. So this is what a fatty acid is right here. But anyhow, even if you don't know what a fatty acid is, you probably recognize that these are all carbon and carbon and carbon-hydrogen bonds. And so this part of the molecule is nonpolar. So that means that soap has a large nonpolar portion, but it also has a portion that has strong dipoles in it, right? The carbon-oxygen bonds, those are strong dipoles. And so we also have a portion that's polar. So you're like, well, what does it do? Soap is polar and nonpolar? Yeah, it is. And that we can use that to our advantage to help us remove dirt and grease from clothing or hands or whatever. If you wash your hands, what the hell is happening? The fatty acid that I had on the previous page looks something like this. Now they had it drawn like this, where you had the carbon, oxygen, okay? And then you had all the carbons like this. Well, they decided to make an abridged version. So this portion, they draw as a sort of a green circle, and then they put a little yellow tail on it like that. So that's the representation of a fatty acid. If you're unsure, look, this is what I mean. You've got the green polar portion, and then you've got a little yellow tail off of it, okay? You're like, man, I hope we draw all the molecules in the class like that. Well, we won't. Anyhow, just like with a crayon, right? Anyhow, but the idea is this, is that when you wash your hands with water, what happens is that the dirt and the grease and the grime go inside what's called a micelle, okay? This is called a micelle, and that interacts with all the hydrophobic portions of the soap, whereas the hydrophilic portion interacts with the outside, and this is where the water is. And if you're like, when I wash my hands, does it form these little balls? Yes, they're so small that you can't see them, but that's what it forms, and then you wash those down the drain. All right. Well, in the interest of time, the only thing I didn't get to was this question here, but I like to put a lot of questions in here. And this is question 1.33. Again, you have the solution, not just the answer, but the solution to this problem. And again, I would recommend looking through all of the practice problems, not some of them, not 80% of them. I would recommend trying all of the practice problems before stepping into the quiz on Monday.